Hi there, this video is going to be a brief overview of the Maxwell-Boltzmann distribution that we'll encounter to describe the distributions of speeds and velocities of molecules in a sample of gas. So you'll encounter the Boltzmann distribution or Maxwell-Boltzmann distribution. Those terms are used pretty interchangeably whenever you're encountering a sample of molecules. So this first video is going to focus on looking at molecular velocities. So one thing that we want to think about is that whenever we have a collection of molecules above absolute zero, we're going to have some thermal energy contained in all of those molecules. In other words, gas molecules are always moving to some extent, either by translational motion, rotational motion, or vibrating. There's always going to be some kind of what we call thermal motion associated with our molecules if we have a sample above 0 Kelvin. So one question you might be asking yourself is, how fast are these gas molecules moving? Okay, there's a variety of ways we can answer that question, though. And the first one we're going to consider is looking at the molecular velocities, which are components of the molecular speed, the overall molecular speed. So one thing to keep in mind is that, remember, when we're talking about velocities, we're talking about a vector that has both a magnitude and a direction. So the first thing we want to do is picture our sample of gas. So we can kind of picture this scenario depicted over here in this figure, where we have some gas molecules that are moving around in our container, bouncing off of the container walls, bouncing off of each other, okay, and they're moving randomly all over the container, again due to that random thermal motion. They're moving in all directions, our X, Y, and Z planes, and when they collide with each other, they may change their direction, and when they collide with the walls, they may change their direction again and exchange energy. So what we have is essentially a giant game of billiards that's being played in our gas container, where the gas molecules are like our billiard balls, and they can bounce off of each other and bounce off of the walls and change their energy and change their direction. The result of all of that motion and collision is that we have a lot of gas molecules that are essentially traveling all at different speeds, different velocities, in different directions. Okay, so the best way that we have to describe this whole situation of our collection of gas molecules is with what we call a distribution of these molecular velocities. All right, so the most common method of describing the distribution of molecular velocities and speeds is, as I mentioned, what we call the Maxwell-Boltzmann distribution. Now, your book goes through kind of the history of how Maxwell and Boltzmann essentially derived these relationships. So we're just going to take the equations as they are. If you're interested in seeing how they are derived, again, just check out chapter 27 of McCory and Simon, or really any other physical chemistry book. We'll go through that derivation for you. So let's just look at the equations that we end up with when all is said and done. So we have a couple of them here that we want to look at. So again, we're just focusing on the velocities. Specifically, we're going to focus on one component of our molecular speed. So we're just going to stick with the X component, but we would have similar equations for the Y and the Z directions as well. So nothing is really going to change there aside from the direction. Okay, so if we're talking about a sample of gas on, I guess, what we would call a macroscopic scale, where we have moles of a sample, then we would be looking at using this form of our Maxwell-Boltzmann distribution for molecular velocities, where we have a function of u sub x, where u sub x is the x component of our molecular velocity. And then we have a constant out front, where we have big M is our molar mass in units of kilograms per mole. R is our gas constant. That's 8.314 joules per mole Kelvin. And we have our temperature, again, always in Kelvin. And then we also have that constant multiplied by this function here, which is actually, we'll see, a Gaussian-shaped function. You might start to recognize that form of function as we go along. But again, that's going to have some similar variables as we had in our constant out front here. So this is the version that you would want to use if you're talking about moles of a gas sample. If you're talking about things on a molecular level, like individual molecules of a gas, then we want to modify that equation a little bit so that we're on a molecular scale. So here we'll just replace the big M with our little m, which represents the mass of one molecule in kilograms. And then our R is going to be replaced by our Boltzmann constant, which is 1.38 times 10 to the minus 23rd joules per Kelvin. We still have our Gaussian function over here, where we've replaced the big M again with our little m, and our big R with the Boltzmann constant. Okay, so same but different. Okay, so one looking at a mole of a sample, the other one would be if you're thinking in terms of individual molecules. Okay, so just to kind of hammer that point home, clearly we have some sort of relationship between our gas constant and Kb, which is our Boltzmann constant. So just to remind you, you'll work with this a bit in your homework. Okay, so we have our big R is related to our Boltzmann constant Kb, will be, by Avogadro's number. Okay, so if we take big R and divide it by our Avogadro's number of molecules, we'll end up with our Boltzmann constant. Okay, so you can do that calculation if you want. So if you take your 8.314 joules per mole Kelvin, divide by Avogadro's constant, you should get out 1.38 times 10 to the minus 23rd joules per Kelvin. Okay, and then we have a similar relationship with big M and little m. Okay, so again, we want to go from big M, our molar mass, to our molecular mass, little m, and to do that, we're just, again, dividing by Avogadro's number. Okay, so those are the basic relationships between our macroscopic and our microscopic quantities. Okay, so big R, macroscopic, big M, macroscopic, Kb and little m would be the microscopic values. Okay, so you may not be able to immediately picture what this function looks like in your head. If you can, awesome, good for you. If not, then you're probably like me and want to plot this to see what it looks like. So here it is. This is a plot of the Maxwell-Boltzmann distribution of molecular velocities for a couple of temperatures. So a couple things to note. Again, just to point out here, remember our function is composed of, this part is just a constant. Okay, those are all constants in there. And then this part here is going to have that Gaussian shape. There's our Gaussian function. Okay, so you may know the Gaussian function as a bell curve. Okay, it has that symmetrical shape about 0. Okay, so here we're seeing that everything's centered at 0. We're talking about velocities, so our molecular velocity component there can take on both positive and negative values. Okay, that's a distinct feature when we're talking about the velocity components of our distribution. Okay, and then the other thing you'll notice with the distribution is that as our temperature increases, the spread of our function increases. So you can see that distribution gets a little shorter and wider. Okay, so as that temperature increases, we start to get more molecules in these higher velocity areas, which makes sense, right? You've got higher temperature, there's more energy to your molecules, they can move a little bit faster. The other thing I want to point out with this function is that it is normalized. Okay, so what does that mean? So this is a normalized function. All that means is that the area under the curve, if I can spell, is equal to 1. Okay, so when we say that a function is normalized, at least in our use of it in physical chemistry, that's just telling us that when we integrate that function over all of the space it can occupy, in this case we would be integrating over negative infinity to infinity, essentially are the bounds for our molecular velocities. When we integrate over all of that space, we should get a probability of 1. So we're essentially calculating a probability when we take that integral of this distribution function. Okay, so we're just saying there's a 100% chance that we're going to get one of the possible speeds for our molecule. Okay, so just remember, normalized function means area under the curve is 1, which means when you integrate, you should get a value of 1. Integrate over all of the usable space, I should say, you get 1. Couple of other features to point out here is that speaking of that normalization, so the area under this curve for 300 Kelvin is going to be 1. The area under the curve for 1000 Kelvin will also be 1. So the total area under each of those curves is the same. Okay, so what that's telling you is that you're not changing the total population of your system. Okay, you still have the same number of molecules, you're just changing how the distribution of their velocities are arranged. Okay, so total area, no matter what your temperature here for a given molecule, for a given sample, that area should always be the same. And then last little tidbit of information is, notice that in the denominator of the Gaussian part of our function, we have the temperature there. Okay, so that essentially dictates the spread of the function. Okay, so when you change the temperature, right, you're going to change the width of that distribution. Okay, and that's because we've got the temperature down there in that denominator. Okay, that's just a typical function of that Gaussian distribution. Okay, I think that's pretty good for the start of talking about our Maxwell-Boltzmann distribution for the velocities, and then we will have another video where we talk about how things change a little bit when we want to talk about the speeds instead of the velocities. So stay tuned for that.